In modern software engineering, complexity is the primary adversary. Brittle integrations, cascading failures, and high maintenance overhead are the direct result of the tightly coupled, imperative logic that underpins most systems. For years, the solution has been better abstraction and tooling. Today, a new architectural pattern is emerging. This pattern is agentic AI. It represents a fundamental shift in how software is designed and built. This video provides a deep architectural dive into agentic frameworks. The goal is not just to define a new technology, but to illuminate a new way of thinking about automation and system design. Stay for the entire exploration, because the conclusion synthesizes everything into a core principle called the agentic shift, a concept essential for anyone designing the next generation of software. To understand agentic systems, one must first understand their core anatomy. An agentic framework is not the AI itself. It is the runtime environment that enables a large language model, acting as a reasoning engine, to execute tasks in the real world. Think of it as an autopilot pattern for software. A standard LLM is a pilot with knowledge, but no access to the plane's controls. The framework provides the cockpit. The essential components of this cockpit are the reasoning loop. This is the agent's central processing cycle. The most prevalent model is ReACT, which stands for Reason plus Act. The LLM first reasons about the goal to form a hypothesis, then selects a tool to take an action. It observes the result of that action and feeds that observation back into its reasoning process to inform the next step. This iterative loop is what allows for complex problem solving. The tool catalog. Well, this is arguably the most critical component from a design perspective. It's a curated, well-documented library of functions, or tools, that the agent is permitted to use. These tools are really just abstractions over external APIs, databases, or other system functions. The agent, honestly, doesn't know how a tool works, only what it does based on its schema. Stateful memory. For any non-trivial task, an agent requires memory. The framework, must provide mechanisms for both short-term scratchpad memory to track the state of the current task, and long-term, often vectorized memory to retrieve relevant information from past interactions or knowledge stores. These three components, the reasoning loop, the tool catalog, and memory, are in fact the foundational pillars that elevate an LLM from a passive information generator into an active, goal-oriented system participant. The adoption of agentic patterns is not driven by novelty, but by a clear architectural imperative. It addresses fundamental limitations in traditional imperative software design, particularly in the areas of resilience and extensibility. Consider the classic engineering problem of automated incident response. An imperative script for this task would contain hard-coded logic. If log contains error A, then execute restart service B. This script is brittle. If the error message changes, or if restarting is not the right solution in a new context, the script fails or causes unintended consequences. A developer must manually update and redeploy the code. An agentic system approaches this differently. It is given a goal: resolve the incident. It is also given a set of tools: query_logs, analyze_metrics, rollback_deployment, notify_on_call_engineer. The agent uses its reasoning loop to analyze the specific incident and select the appropriate sequence of tools. This design is architecturally superior for two key reasons. First, resilience through dynamic response. The agent can adapt its plan based on real-time observations. If a rollback fails, it can observe the failure and escalate to the human on call, a level of fault tolerance that is honestly pretty difficult to hard code. Second, extensibility by composition. To enhance the system's capabilities, one does not modify the agent's core logic. Instead, a new tool is added to the catalog. For instance, adding a quarantine_instance tool instantly gives the agent a new potential strategy for problem solving without requiring a rewrite of the agent itself. A robust open-source ecosystem provides the foundation for building these systems. Familiarity with the leading frameworks is essential for any architect or developer in this space. LangChain is a highly modular and extensive framework, and it's noteworthy for its LangChain Expression Language, or LCEL, which provides a declarative syntax for composing agentic chains. Llama Index is specialized for building agents that reason over private or external data. It offers the most advanced open-source toolkit for retrieval augmented generation, or RAG, which is a critical pattern for knowledge-intensive agents. Microsoft AutoGen introduces the concept of multi-agent conversational systems. This framework allows for the creation of multiple specialized agents that collaborate to solve a problem, enabling a powerful separation of concerns. Crew AI builds upon the multi-agent concept with a focus on process orchestration. It provides a structure for defining agent roles and sequential or parallel tasks, making it suitable for automating complex business workflows. Agency is a forward-looking framework built on web standards like WebAssembly. Its focus on portability and interoperability addresses key enterprise concerns for long-term architectural stability. Implementing a production-grade agentic system requires a disciplined architectural approach. Beyond selecting a framework, these 5 pillars are critical for building systems that are secure, reliable, and manageable. First, comprehensive observability. Full transparency into the agent's reasoning process is not a feature, it's a core requirement. The system must log every thought, action, and observation to create a trajectory trace. This is the primary mechanism for debugging, auditing, and performance analysis. Second, formalized tool governance tools are the primary interaction surface with other systems and must be treated as first-class architectural components. This requires a formal catalog with versioning, schema definitions such as open API specs, and strict access controls. Third, secure execution sandboxing agent-generated actions, particularly code execution or shell commands, must be treated as untrusted input. These actions must be executed within isolated, ephemeral sandboxes, like Docker containers or WebAssembly runtimes, to prevent unintended system access. Fourth, deterministic cost and performance controls. The iterative nature of agents can lead to unpredictable costs and latencies. It's essential to implement circuit breakers, token counters, time limits, and caching mechanisms to prevent runaway processes and ensure predictable performance. And finally, human-in-the-loop integration. For any action that is destructive, costly, or irreversible, a human approval step must be designed into the workflow. This is not a fallback, but a deliberate security and control feature of a mature agentic system. This exploration of agentic frameworks leads to a crucial conclusion: a fundamental change in the philosophy of software design. This is the agentic shift. Software engineering has largely been dominated by imperative logic. The developer explicitly defines how a task is to be accomplished step by step. The agentic shift is a move towards declarative, goal-oriented systems. In this new paradigm, the focus of the developer's work changes. The primary task is no longer to write the step-by-step execution logic. Instead, the work is to architect the environment in which an autonomous agent can succeed. This involves 3 core responsibilities: define a clear goal or objective, construct a robust set of tools the agent can use, and engineer the safety guardrails to constrain its behavior. The system is told what the desired outcome is, not how to achieve it. This is a more powerful, scalable, and resilient model for building complex software. Understanding this principle is the key takeaway. It's the mental model required to move beyond simply using AI as a feature and to begin architecting truly intelligent systems.